Hello there, hi, my name's Desmond Aubrey. I'm from Rarefied Technologies, Southeast Asia. We call ourselves RareTechSEA just to keep it simple. What I want to do today is start on a series discussing modular shell and tube heat exchangers. You know, classically we've had shell and tube heat exchangers around for a very long time, and they've often ended up being very big devices that are quite complicated. But the classical design of these would have a single segmented baffle in the shell side, and then that would actually have certain cutout which the fluid can go through, and then these are then placed alternately, typically with the cuts horizontally. It's a very inefficient process very often because the shell side is not properly matched with the tube side. About 1960s, a Swiss German by the name of Gesalter ended up coming up with a modular concept, and the idea was to be able to take almost off-the-shelf components like the shell and tubes, and instead of welding the tubes into the tube sheet, the idea was to use elastomeric seals, different types of seals of elastomers, and then to push these between certain pressure plates, and the pressure plates would then squeeze the seals, and the seals then squeeze against the shell or against the tubes and so on. And this actually allowed, it allowed in fact very thin tubes to be used if necessary, which is good for heat transfer, and obviously brought costs down. One stage, what actually happened in South Africa, historically what happened is Gesalter had a deal with a British guy who then introduced this to a company that he worked with. And they then started to make the first units of these. But they were very simple units, South Africa was, and but the Gesalter had actually made very complicated sugar type systems, quite amazing actually. If I see old pictures, and I'll show those in a later presentation, and they were really quite works of art, and they worked very well in the sugar industry. Now the idea behind modular shell and tube is that you can take standard components, put them off the shelf, take them, put them together, and make up quite complicated structures, which then allow you to optimize fluid flow, essentially tube side and shell side. So it's actually a very interesting technology, and I got into this. I actually worked when I was a young engineer. I'd worked for a big petrochem company, and then making chemicals and so on. And then I came across this heat exchanger company and really fell in love with the products. It was a small little company in South Africa. What had happened is the original British guy, they had actually, the parent company, sold it to two partners. One was an engineer that worked for them, ex-Royal Navy, a very smart guy actually. And the other chap was the money guy, and this was now going to be their retirement. So they then started up this little business, and it was called Transheat Pty Limited in South Africa. Very small, and kind of I got in there. I was their first permanent, let's call it, design engineer. And during that time, we ended up with quite a lot of challenges because the technology had been originally supplied to these people on the old Texas Instrument calculator using magnetic cards. And what would then happen is the owner was, and he couldn't actually see what the code actually was. He could just check the results. So this chap, his name is called him John, he then developed a method to try and come up with something similar and develop theory. All right, which then, because what you're going to see later in this particular shell and tube design, we have a very special spiral baffle, which is unlike anything else in the world. Right? It's very different. And then to try and categorize what that thing's actually doing, there was no theory. You still don't have theory today, even at universities. Professors rack their brains; they don't understand it. But it's fun. It's classic. So anyway, what happened is I worked with them for a while, and they had promised part ownership of the business, and it didn't work out because you had two equal shareholders and they didn't want to give up anything. So I moved on with the rest of my life. And then years later, after having traveled through something like 36 countries on business as a consulting engineer internationally, I came back to South Africa. And in the meantime, this particular outfit had been bought by a huge company and just became one of their divisions. And they were running into all kinds of problems, with these big companies that acquire businesses. They eventually kill them, So I took over the running of the division as a consultant for a while. And then they said, listen, we want to stop the operation because there's too much, the staff that had been taken on had become very complex and complicated and very difficult to manage. So then I made them an offer for the princely sum of 1 South African rand, and effectively I put a team together of builders and myself in a small business. And we then I did all the technology transfer and acquired all the technology from, legally from what was effectively Transheat's know-how. And the technology had advanced actually quite a bit after the time that I had originally been there. So there were a few new tricks into it, which were actually a lot of fun. And we had a lot of success actually while I was there. I remember one particular application where they had, it was actually done in the sugar industry. And there they actually still used steam turbines, to drive certain parts of the process. But the problem is you had to cool the oil for these turbines because they were, if the oil control is not correct, the turbine will burn out, the bearings will burn out. And I remember this was always a problem for what the guys previous to me had actually put together, and some of the exchanges just didn't work. So I actually went down there and I chatted with the engineer and got to understand his process, and I then designed him a special set of oil coolers which were able to handle, the same cooler could handle 2 different oil applications. And he was one of these remarkable people that actually measured the mass flow rates and the temperatures in and out of these exchanges. He's the only guy I'd ever seen do that. Very thorough guy from Zimbabwe, really good. And so anyway, these units worked very well. We had other applications where they had persistent problems with seals. What I would then do is go through and understand the heat transfer, what's going on in conducting the heat in through the pressure members and so on, and redesign them, and then you wouldn't hear anything more. So we did a lot of very good work, and then a lot of work also for the mines. What had actually happened is during my period originally with Transheat, they were coming up with an elution process, and consultants came to us and said, well, can you design us a set of exchanges? What we envisage is fluid coming in, it then goes through a heater, we might have goes through a heater, then goes through the tower as hot fluid. Coming back, we might try and recover some of the heat through an interchanger or economizer, and then have a trim cooler at the exit of all of that. So there was going to be a bunch of exchanges. So, and they were looking for the least capital cost at that stage for the 3. So I then did work on that. And eventually I realized I don't actually have to have a cooler at all. All I needed essentially was an interchanger, and I needed a heater. And I then basically stepped through at different temperatures until I actually got to the optimum point. And from that became the standard for these units. So they were essentially heater sets and interchanger or economizer sets, which were novel. And so my know-how kind of hung around there even after I'd left, And actually, while I was there, I actually wrote the software. I wrote the code. In those days, all we had was something like Quick Basic, And I wrote all the code to design these units. There was a range of different options and modules, and single phase and then 2-phase, as in condensing or evaporating, different modes. I wrote all that software for it. And so when I came back to this company many years later, I then grabbed that code. They didn't know how to get to the original source code because I had originally saved it in a certain format, which they didn't understand. So I was able to extract my original code. And then I went through and I started to adjust, add a few tweaks to the program and so on. I noticed in the intervening years, the other engineers hadn't managed to make much headway. So I put quite a bit of work into that. So the software was then quite thorough. And what I then did is I moved it into a later version, which compiles nicely and everything. And it can run on Linux, it can run on Windows, and so on. Anyway, long story short, we acquired this company and all its technology, and so I'm now the technology director for this little small, what we call closed corporation. Anyway, lo and behold, we had to make a trip back to Laos. My wife's from Laos, and her mom had passed away. And during that time, the partners got greedy. And what happened is the one lady who was a partner, her husband they were doing manufacturing as well, and they literally, because there were three of us in the business, they hijacked the bank account, and they ended up stealing a lot of money from me, and then trying to use lawyers to chase me away, and that really was quite a story. But I had acquired all the heat transfer technology, all the digital technology. I had everything available to me on these units, which I said to them, I'm not giving back. I was very kind. I gave them a running version of the software, no source code, but a running version, so that they could never complain. And then I have kept all the know-how. I've got drawings that go all the way back to, right to the start, to Gesalta, moving onwards through the various, let's call it incantations or incarnations or life cycles of this particular product. And what I hope to do with the presentations that are coming up, and I'll work through a few slides, and I'll stop, and then I'll move on to other in steps, so I can make sense of the whole thing. If you're still listening, all right. So in reality, I still own the technology to these products. In South Africa, they go under the brand name of Tronson, which was what the brand that I owned. I actually owned the brand. I actually purchased the brand rights in South Africa through my intellectual property attorneys. So all kinds of tricks they were trying to do behind my back, but they never succeeded. But I've kept all the technology, and I'm the only guy in the world that has all of this. And I wrote a paper also on how these units worked in the mining game, because it was a real fascinating application, because it actually has a very fine silt in there. But we'll talk more as we go through. I'll just yap along as we go through. So let me try and see if I've got it right. I'm going to step through the presentation. Let's see if it does it right. I'll probably have to press it or something. What's it? There we go. So let's talk about the kind of applications we can use these exchangers in. So, for instance, the gold elution process, where what this is typically you're taking the tails, or sometimes even the tail dumps from original gold extraction. You've got this mixture of stuff. A lot of it's silt and sediment, actually. But the fluids are very close to water, to be honest. So what actually, and I'll go through this later, this actually goes through, firstly, the economizer, through a heater, through the elution tower, cools slightly during the process. You've got carbon and everything in there. Comes back through the economizer, recovers a lot of the energy, and then it's cooled at the same time. It's heating in the incoming feed, and then it goes out to these electrowinning cells. But they have to be carefully controlled. If you don't get it right, you mess up the electrowinning cell. And then we have things like thermal oil heaters. Again, with elastomeric seals, you have some limits as to how high you can go. So typically there are some tricks that we apply to the seals in terms of insulation, or backer seals as we call it, to get to the higher temperatures. Things like condensers, very straightforward. You can condensing fluids. They did a bit of work with HVAC, but HVAC is tricky if you're using elastomers, because some of these refrigerants get through anywhere. And it's quite tricky when you've got seals. But of course you can do it, and I've built them for this unit, but you've got to know what you're doing. And then things like acid heaters and coolers, plenty of those. You might want to cool acid, you might want to heat acid, you might want to interchange fields. But acid's tricky, because if you get the properties wrong, you can end up with some major corrosion problems. But you get other funny things, like if you use oleum, which is essentially fuming sulfuric acid, you can use mild steel. It's quite amazing. So you really have to know what you're doing. Things like waste heat recovery, you can recover waste heat with this. Compressor, a lot of this kind of work, after coolers, intercoolers from the compressor, cooling air, for instance, also sometimes compressor oils that you actually cool, like and also like turbines and so on. We use these after coolers and intercoolers and so on. And storage vessels, you'll see a slide later where you actually take these units and mount them on the side of the vessel if you want to, or you can mount them on the ground. And then you can actually cycle the fluid through the vessel and heat it up gradually. And you can also use, principles of plug flow, whatever you like, to actually manage the heat in that vessel. So you can have heating and cooling. It's quite nice for that. Okay. Petrochemical heat transfer, again, you've got to be careful on the specs that the people want from you, but typically we've done work for petrochem. Oil coolers and heaters, well, that's very standard fare. Now, why is that? Because the transferring heat into and out of oil is extremely difficult. And what happens typically is you get laminar flow. Let me explain. When you come to fluid flow, we've got three regimes. We have the slow flow, treacly type, honey type flow, which we call laminar flow. Very poor heat transfer. Low pressure drop, but poor heat transfer. Then on the other end of the thing, we end up with a fully turbulent flow, which has much better heat transfer but higher pressure drops. And in between, we've got a zone we call the transition zone. And frankly, there's no theory for that zone at all. So engineers are told, well, don't go laminar, go into fully turbulent, make sure you stay up there. So we actually control that through a thing called Reynolds number. But oil coolers are notorious for running laminar because the pressure drops end up so high. So then how on earth do you get the heat to get into it? So typically we put, for oil coolers and heaters, we put that oil on the shell side and then we create mechanical turbulation to actually get the mix in that you require. So it's quite tricky. Closed circuit coolers, yeah, plenty of that, for engine jacket coolers. If you've got these big standby engines, South Africa right now is going through a lot of problems with electricity. So you have these huge standby engines, and then you've actually got to keep the jacket cool, otherwise it blows up. So you've got to have this external cooler through which you have cooling water, typically from a cooling tower or something like that, and that keeps the engine running, keeps it cool. Water heaters and coolers, plenty of those. Coffee extract heaters and coolers. So people are making coffee, granulated coffee and so on. They need these things. Chocolate heaters work in that as well. Funnily enough, tomato sauce, all these kind of they're non-linear fluids. In other words, they're not non-Newtonian fluids. Most fluids, like water and so on, we call Newtonian, and they behave themselves. But these non-Newtonian fluids don't behave themselves, and so you've got to really understand what you're doing when you're designing exchangers. There's no plug and play. You just take a computer program and you plug in and say, well, I've got to heat a good unit. No. You've still got to be a good engineer, otherwise you're going to mess it up. Juice coolers, yeah, things like, fruit juices. They use an apple juice carrier typically, or grape juice as a carrier and so on. And so you've got to keep these kind of fruit juices cool, and this is perfect for that because you can strip them. Calorifiers, as other words, where you're using steam to actually heat water. And you can do it through a storage system. I've got drawings in that for these things where you actually pass steam through the tubes and the calorifier sitting inside the actual vertical vessel. Or you can have them sitting on a circulation where you circulate the water carefully. You've got to be careful when you work with water tanks and so on to not mix the flow. So you've got to create a plug flow situation. So again, you have to know what you're doing. And if you don't know what you're doing, you're going to end up with a mess. Okay. So let's see. Now, let's talk about novel technologies. Novel as in very different. Okay. How are we for time? Let's see. I'm just trying to make sure we can take 20 minutes off. So novel technologies. What we've got here is a single module. We call it a single module. And I'll talk through more detail later on what's involved here. But you've got your shell, and to that you've got certain plates that are attached to the shell, and then of course it keeps the headers in place. These individual things are called headers. All right. And then you've got bolts that hold it together, and then you pull it all up nice and tight, and the elastomeric seals then swell back and they close off so that you don't get any leaks. And then we have the thing we'll talk about later over here, which allows, if there's a problem, actually allows you to escape fluid out and you don't mix the two streams. But that was the original design. Very simple, looks simple, but you can then now take this into multi-module type operations, which is fantastic, and this is where it really starts to come into its own. Now, the novel technologies involved in this are spiral shell side baffle, which we'll discuss a little bit more later. Truly novel, and I've done a lot of work with the original arrangements, and I've also done a lot of work with alternative arrangements, which actually are far more efficient. But it's because you have to understand spiraling flow and getting the actual fluids to do what they're supposed to do. The elastomeric tube seals, again, there's a range of elastomers that we use depending on the application. If it's oils, it's a certain elastomer. If it's high temperature, it's another elastomer. This story about vented headers that I was talking about there, I'll discuss it in more detail later. We also have an option of a single header where we in fact get rid of one of these and we actually put the ins and outs sockets on top of the shell directly. Modular construction, you can strip this thing down. The beauty about these on the mines is that if they foul up, they don't foul up very easily, funny enough, but they work for a long time. And if they want to strip them, they can strip them and rebuild it. Some of these units have lasted 30 years, okay, by rebuilding in a very difficult situation. Standard components off the shelf. So typically most of the components, the internals here and everything, are off the shelf. The headers can sit on the shelf, everything else, except the way you set up the shell and then the tube length that you use for the application. And then there's two units. Typically the U5 is the most common, but the U3 is a smaller unit that they developed a little bit later, similar to this. It's not as efficient as the U5, but we used a lot of that for oil coolers, small oil coolers. They were actually quite nice. And then tank systems. You have tanks and external cooling and heating. Okay, so what I'm going to do, I'm going to stop at that point, and then I'll pick it up next time with a little bit more detail, and we go through step by step, and I hope you found it interesting. Anyway, thanks for now. Bye-bye.